Hi, in this case we are going to talk about QRS complex. First we have definition. It's a name for the combination of three of the graphical deflection seen on a typical electrocardiogram. It is usually the central and most visually obvious part of the tracing. How to read an electrocardiogram. Now we're going to watch a video where we're going to focus on the QRS complex.
And when you look at an electrocardiogram, it looks kind of like this. And you've probably seen this. Normally when you see this, there's a beep associated with it, and there's no beep in this animation, but you get the point. Now what we're going to do is we're going to look at this, and we're going to look at each component of the electrocardiogram. So let's look at it right now. So we're looking at an electrocardiogram, and you can see that we have a number of things. We have this peak over here, and we're going to call this the P wave, this peak right here. And then we have this section that we're going to call the QRS complex. And then we have the T wave, and sometimes we get this U wave. And we're going to talk about what these different waves show. So the P wave, we've looked at how the SA node generates the signal, and then that signal spreads to the muscle cells in the atria. And what this P wave shows us is the depolarization of the atria. Okay, so when the atria depolarizes, we see this peak. Then we have the QRS complex, and you probably guessed it by now, but this shows the depolarization. Polarization of the ventricles.
Like it said in the video, it corresponds to the despolarization of the right and left ventricles of the human heart. The QRS waves occur in a rapid succession, do not all appear in all leads, and reflect a single event, and thus are usually considered together. Now we're going to watch a video about what is QRS electromagnetic waves.
You are talking about pulsating magnetic fields right now. What has QRS in quantum medicine to do with that? QRS is the abbreviation for quantum resonance system. So the quantum medicine works with the knowledge of the quantum physics. A quantum is a particle without mass, which can swing in very different frequencies. We know this from photons or light. In this case, the oscillation is short wave with a high frequency. If the frequency is low and the oscillation is long wave, we have electromagnetic fields. And what is quantum medicine concretely? Very simple. The concept quantum medicine is the conceivably most precise definition for the action of electromagnetic waves and also pulsating magnetic fields for the influence on biologic processes in the body. So, pulsating magnetic fields earn the definition quantum medicine if they, with help of special frequencies, treat body cells in organs and in fact diseases. In other words, without special frequencies, a biological influence is hard to imagine. So QRS is really the original. Yes, that's right.
Now we have the etiology. The X-Purkinje specialized muscle cells coordinate the despolarization of both ventricles nearly simultaneously. If they are working efficiently, the QRS complex is 80 to 120 milliliters duration. This is represented by 3 small squares or less at the standard paper speed of 25 millimeters per second. Q wave. Normal Q wave, when present, represent the polarization of the interventricular septum. For this reason, they are referred to as septal Q waves and can be appreciated in the lateral leads 8 and 8BL, B5 and B6. Pathological Q waves occur when the electrical signal passes through stone or scarred myocardium. As such, they are usually markers of previous myocardial infarctions with subsequent fibrosis. QR duration, amplitude. The duration and amplitude of the QRS complex are useful in diagnosing cardiac arrhythmias, conduction abnormalities, and other disease states. Now we are going to watch a video about how to do this.
Measure the duration of the QRS complex. You look for a complex with a neat beginning and ending. You place your caliper on the Q wave and the second point of the caliper on the end of the QRS complex where it meets the ST segment. You then slide the caliper down and count the number of small squares between the tips of the caliper. In this case, there are 3 small squares. Each square is 0.04 seconds, therefore the QRS duration is 0.12 seconds in length. Let's examine the compensatory pause. We do this by first measuring the R to R interval preceding the premature complex. Spread the calipers and place them on the 2R waves preceding the premature complex. We then move the calipers forward, rotating them, and see that the R following this lands on the caliper tip. Therefore, the R to R interval, which bridges the premature complex, is exactly 2 times the preceding R to R interval. This defines a compensatory pause.
R wave progression. Looking at the precordial leads, the R wave usually progresses from showing a RS-type complex in V1 with an increasing R and decreasing S wave when moving towards the left side. There is usually an QR type of complex in V5 and V6 with the R wave amplitude usually taller in V5 than in V6. The transition zone is where the QRS complex changes from predominantly negative to predominantly positive, and this usually occurs at V3 or V4. Monomorphic and polymorphic. Monomorphic is when all QRS waves in a single lead being similar in shape, and polymorphic the QRS change from complex to complex.
We are going to have our sensor, the thing that picks it up, will be sitting right down here, kind of like an eyeball. It's going to be looking at the heart in this direction. Rule number 1 is going to be, let's see, let's put rule number 1 over here. 1. If it sees electricity move towards it, then the deflection will go up. When the electricity ends, the deflection will come back down again. Rule number 2 is, if it sees electricity move away from the eyeball, the deflection will go down, and when the electricity ends, it will come back up here like this. Rule number 3 is going to be more electricity equals more deflection. So, if we have a little bump like that, a big bump like this, we know that this one is more electricity and more tissue relative to this. Okay, let's move down here and we'll start again. Here we have our eyeball, and it's looking at the heart. We're going to go through a normal conduction. So as the electricity moves from SA to AV, we would expect there to be a bump up, but then the electricity goes into the AV node, and the eyeball can't see it anymore, so it goes down like this. We know that the AV hangs on to it for about 1/10 of a second, so we have this flat line, and then it sends the electricity down the bundle branches. That's moving towards the eye, so we get a deflection up. It's going to move away like this, and now we have to get a deflection down, and then the electricity ends. And then this thing happens that's kind of hard to explain unless you think back to the movement of ions, which is really all we're measuring here. Now,
Not every QRS complex contains a Q wave, an R wave, and an S wave. By convention, any combination of these waves can be referred to as QRS complex. However, correct interpretation of difficult EKG requires exact labeling of the various waves.
If the premature QRS complex arises in the ventricles, this will not result in a depolarization of the SA node. Therefore, the SA node will continue to fire spontaneously at the rate that was occurring before the premature complex. Therefore, when we look on the strip, we will see a pause following the ventricular premature complex, which compensates to allow the heart to begin depolarizing and beating at the same rate as before. We can determine this on the graph paper by measuring the R to R interval, both before and after the premature ventricular complex. First, we measure the R to R interval for the two normal complexes immediately preceding the premature ventricular complex. We then measure the R to R interval that are crossing the premature complex. We'll note with a compensatory pause that the R to R interval following the premature ventricular complex is exactly 2 times the R to R interval before the premature ventricular complex. This is defined as a compensatory pause.
Thanks for your attention.